Just as Nicholas Copernicus presented the heliocentric model, another remarkable revision of our comprehension of the cosmos could arise, igniting a discussion known as the crisis of cosmology. This crisis is characterized by significant inconsistencies in our measurements and perceptions of the universe's fundamental traits, such as its age, size, and rate of expansion. Neil deGrasse Tyson has observed that the discovery of the James Webb Space Telescope, JWST, has effectively concluded this debate with an image that defies conventional physics. So, what precisely is this crisis, and how does the James Webb Space Telescope contribute to it? Well, contributing is somewhat of an exaggeration. It's more like a review that has been in progress. The crisis denotes a moment when our comprehension of the universe is questioned, particularly regarding its age and dimensions, which are linked by a considerable margin of uncertainty. The introduction of the JWST has been vital in this regard. Prior to this breakthrough, we were restricted in how far we could observe the early universe, but with the JWST's enhanced capabilities, astronomers can investigate far more distant galaxies, offering us new insights into the universe and challenging some of our earlier notions. This advancement allows us to look further back in time, closer to the Big Bang, and examine galaxies as they were forming, providing essential data that can either validate or dispute our current models of the universe. To understand the crisis in depth, it is crucial to revisit the standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter lambda CDM model. This model has been quite successful in elucidating various aspects of the universe, from gravitational lensing to the structure of the cosmic web and the evolution of galaxies. The lambda CDM model suggests that the universe began with a Big Bang, followed by a period of rapid inflation, and has been expanding ever since. It incorporates elements such as dark matter, which exerts gravitational influence, and dark energy, which propels the accelerated expansion of the universe. However, every new observation, especially with instruments as sophisticated as the JWST, raises the possibility that our existing model may be flawed or require revision. The lambda CDM model makes specific predictions regarding the characteristics and behavior of galaxies at different epochs of the universe's history. For example, it forecasts that galaxies in the distant past should be smaller, less developed, and composed of fewer heavy elements compared to those we observe in our local universe. This is due to the fact that heavier elements are created in the cores of stars and distributed through processes like supernova explosions, which take time to occur. The description you provide pertains to how the standard model of cosmology predicts the movements within groups and clusters of galaxies, as well as the characteristics of the cosmic microwave background, CMB. As we delve deeper into the past, according to this model, galaxies should be smaller, bluer, less developed, and less rich in heavy elements at cosmic distances beyond our own. This would lead us to expect to encounter epochs of the universe devoid of visible stars or galaxies. However, scientists have discovered contradictory evidence that challenges these predictions, resulting in a crisis in cosmology. The crisis in cosmology centers on the uncertainty surrounding the age of the universe. Different measurement techniques yield different results, causing cosmologists to struggle to reconcile these discrepancies. To address this issue, scientists employ several methods to ascertain the age of the universe. One approach is the study of cosmic background radiation, which involves unraveling the history of the universe's expansion and utilizing mathematical models such as the Friedmann equations based on Einstein's theory of general relativity to determine the expansion rate and, therefore, the universe's age at various times. The CMB, a remnant radiation from the universe's early days, is an essential tool for this measurement. Detailed maps of the CMB, such as those produced by the European Space Agency's Planck mission, provide valuable insights into the universe's composition. However, these maps lack data on dark energy, a major component of the contemporary universe. Despite this limitation, scientists can employ Friedmann's equations alongside other observations to estimate the universe's expansion rate at different times and ultimately determine its age. The Friedmann equations describe how the universe expands, accounting for the density of various components like dark matter, dark energy, and ordinary matter. By analyzing the CMB, scientists can infer the conditions of the early universe and extrapolate the expansion history up to the present day. Another method for determining the universe's age involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles because they possess a known intrinsic brightness. By comparing their known brightness to their observed brightness, astronomers can ascertain their distance and, consequently, the expansion rate of the universe at various times. This technique, employed in the 1990s, played a pivotal role in the discovery of dark energy, which is now fundamental to cosmological measurements. It is especially useful for determining the Hubble constant, a measure of the universe's expansion rate. Although not precisely constant, the Hubble constant is crucial in charting the expansion of the universe since the Big Bang, roughly 13.8 billion years ago. It has been noted that the cosmos has been growing steadily. NASA has emphasized that the implications of this rate are significant. If the expansion is decelerating, it suggests the presence of an unknown force, potentially dark matter, influencing this process. Conversely, if the expansion rate is accelerating, it could indicate the presence and effect of dark energy, promoting the universe's growth. In January 2008, 18 scientists made an intriguing discovery. Although several telescopes indicated that the universe's expansion rate varied depending on the observation point, the Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope recorded a slightly lower expansion in more distant regions. This discrepancy in measurement underscores the vast scale of the universe and recalls the groundbreaking work of Edwin Hubble, who first proposed the universe's expansion rate in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, indicating that the universe is indeed expanding. This finding was one of the cornerstones of modern cosmology. Now, considering the expansion of the universe regardless of your cosmic position, you would witness the same occurrence at the same velocity, adhering to the Hubble expansion rate. Initial computations relied on limited information, but with advancements in technology, such as the Hubble and Gaia telescopes, we have been able to observe additional variables and enhance our measurements. Other telescopes employ readings from the cosmic microwave background, CMB, to determine the constant, though this method has its constraints due to the scarcity of supernovae for distant observations, limiting our perspective on the universe. Since the identification of dark energy in the 20th century, researchers have faced challenges stemming from inconsistencies between these two methods regarding the universe's age and its expansion rate. As measurement technology improves, smaller discrepancies emerge, propelled by the creation of more sophisticated systems. This development, paradoxically, raises further questions instead of yielding definitive answers. Although the variations are slight, with estimates differing by only 10 to 20 million years, considering the universe is around 13.77 billion years old, it still merits extensive examination. One possible reason for this inconsistency could lie in potential inaccuracies in our measurements of the CMB. Despite being among the most precise measurements available, it has undergone rigorous testing since its launch in 2003 to confirm its reliability. Another viewpoint proposes a possible gap in our understanding of dark matter, suggesting it might fluctuate over time and could be linked to dark energy or some other unidentified factor. This notion has prompted numerous investigative studies. The reliability of supernova measurements is also under scrutiny, as the complexity of stellar explosions can introduce uncertainty into the models we employ. Clarifying this uncertainty in supernova models could assist in reconciling the measurement discrepancies. This crisis in cosmology has been further intensified by the emergence of the James Webb Space Telescope, JWST. According to Neil deGrasse Tyson, the JWST has detected objects in the universe that challenge our current understanding. This suggests that our scientific framework may need a comprehensive reevaluation, but the challenge lies in determining where to start. To appreciate the scale of this scientific upheaval, let's look at the origins of the universe. Roughly 150 million years after the Big Bang, stars, black holes, and star clusters began to form, possibly as early as 50 to 100 million years later. However, these events should be relatively uncommon. What remains unclear is how frequently galaxies developed in subsequent times, encompassing events between 200 and 400 million years after the Big Bang. Recent images from the JWST reveal galaxies that are significantly more distant and therefore older than the standard cosmological model predicts. This inconsistency suggests that our model requires a significant overhaul. The realization that the expanding universe depends on galaxies represents a groundbreaking development. JWST imagery showcases galaxies that formed much earlier than current cosmological models suggest, igniting a crisis in the field. This issue relates to galaxies and redshift, a common measurement in cosmology. According to the Standard Model, hydrogen began to emerge 400,000 years after the Big Bang when protons and electrons combined, resulting in hydrogen recombination. This transformed the universe into a blend of hydrogen atoms with some helium and residual background radiation. The gravity of the radiation then influenced minor fluctuations in this hydrogen gas, gradually collapsing them to form the first stars. These early stars, primarily composed of helium and hydrogen, participated in nuclear fusion, generating heavier elements such as carbon and nitrogen. These elements were crucial in galaxy formation, as they absorbed heat and emitted cooling photons, facilitating the accumulation of gas into galaxies. The process of galaxy formation and evolution is intricate, involving multiple stages, including the merging of smaller structures into larger ones and the continual formation of new stars from interstellar gas. However, the JWST has detected galaxies that formed much earlier than predicted by our existing models, indicating that we may need to revise our understanding of the early universe. This new information challenges our current theories and raises inquiries about the processes that led to the formation of the first galaxies. The ramifications of these discoveries are profound, as they could prompt a significant shift in our understanding of the universe and its origins. In summary, the crisis in cosmology highlights the challenges and uncertainties we encounter in grasping the universe's fundamental characteristics. The James Webb Space Telescope has provided valuable new data that questions our existing models and encourages a reevaluation of our theories. This ongoing cycle of discovery and revision exemplifies the dynamic nature of scientific inquiry and the constantly evolving nature of our comprehension of the cosmos. The crisis in cosmology not only affects our understanding of the universe's age and expansion but also raises questions about the very essence of reality. Recent discoveries challenge the foundational assumptions of many cosmological theories. For instance, the presence of galaxies that formed significantly earlier than previously believed indicates that our timeline for cosmic evolution may require substantial adjustments. Furthermore, data from the JWST suggests that the processes driving galaxy formation could be more complex than current models imply. These findings particularly call for a reassessment of how galaxies interact with their environment, including the influence of gas inflow and outflow on their development. Such interactions may affect star formation rates, leading to a new understanding of how galaxies evolve over time. Additionally, the relationship between dark matter and ordinary matter is becoming a focal point for further investigation. Observations suggest that dark matter might play a crucial role in galaxy formation and behavior, impacting how visible matter is distributed within galaxies. As scientists delve deeper into this relationship, they may uncover new physics that could bridge the gaps in our current knowledge. Astrophysical simulations are also advancing alongside observational improvements. These simulations can incorporate fresh findings from telescopes like the JWST, enabling researchers to model galaxy formation and evolution with greater accuracy. By integrating various astrophysical processes, such as supernova feedback and cosmic gas dynamics, simulations can provide insights into the conditions that led to the formation of the first galaxies. The interplay between observational data and theoretical models is vital in refining our comprehension of cosmology. As more data becomes available, scientists will have the opportunity to test established theories against new observations. This iterative process is fundamental to scientific progress, allowing researchers to adapt and enhance their models to reflect the complexities of the universe. Ultimately, these discoveries underscore the dynamic and ever-evolving nature of cosmological research. Each new observation can serve as a catalyst for deeper exploration, leading to revisions that could redefine our understanding of the cosmos. As we continue to investigate the universe, the potential for groundbreaking revelations remains extensive, sustaining the spirit of inquiry in the field of cosmology.